Good morning, everyone. So I'm Clarissa Toscano, and my research project topic is radiation protection in nuclear submarines, strategies, challenges, and emerging technologies. Now, you guys might be wondering why this topic, why not something related to radiotherapy, dosimetry. So, and everyone knows that since nuclear submarines, they also have shielding, they require dosimetry, they also need to have relative effectiveness as well, which are all the principles for the medical physics. So that's why I choose this topic, which brings me to my background and motivation. So, nuclear submarines have unmatched stealth and endurance. So, they also play a major role in defense and national security. So, because they can remain submerged for months, they also can operate silently, and they also have visuality, so they cannot be visible to everyone as well. Also, the only difference between the submarines and the land-based reactor is that the submarines, they operate in the confined environment, and they also have the unique neutron gamma radiation fits. So since they operate in the confined environments, the crew are very close to the reactors, and that is why the radiation protection in nuclear submarines is really, really important. So the aims and objectives for me were to identify the effective shielding materials and reactor designs. So we do know that lead and concrete are the traditional shielding materials, but in submarines, it's quite where weight is a constraint. We need to have something that is really lightweight as well. Next is to assess crew monitoring and dosimetry technologies. Since evacuation is not an option in submarines, we need to have effective and we need to have something that can give us instant readout. The next is to evaluate the challenges faced by submarine crews in maintaining the radiation safety. Next is to review the emerging technologies. So that is in terms of AI, that is in terms of robotics, and that is in terms of composites. And next is to identify the gaps and to know where we're headed in the future. So to conduct this literature review and to conduct this proposal, I followed basically three steps. So first was to search along the database, and the databases that I used were the Web of Science, Science Direct, the IEA publications, and Scopus. And to conduct this search, so the strategy that I used was to use the keywords, so such as nuclear submarine, naval reactors, such as marine radioactivity, shielding, dosimetry, and I also added in some of the Boolean operators as well. And after I got all these articles and publications, I refined them into if they were conducted in the last 10 years, if they were relevant to the topic, and if they were peer reviewed. So all the papers that I got, I included the ones that were peer reviewed and which were directly addressed by this topics. So that was submarine or shipboard radiological protection, occupational dose or shielding simulation, marine contamination or monitoring systems, and emerging radiation mitigation technologies. So when I conducted this literature review, so the themes and the main terms that were highlighted were this. So that had dosimetry and crew monitoring, shielding materials and structural innovations, simulation and computational modeling, accident response and environmental monitoring, and policy regulation and governance. So let's briefly get into all these five terms. So first is advancement in crew monitoring and dosimetry. So in nuclear submarines, they mostly go for TLDs and film batches. But as we all know that TLDs and film batches, they don't offer immediate readout. So they cannot have the real-time monitoring as well. So Chatterjee in his literature review said that we have been developing the CMOS dosimeters, that is the compact metal oxide semiconductors. So they enable the real-time monitoring. So in the situations where accidents or there are some problems with the shielding, the crew will be able to get the instant readout for the dose. So if they are overdosed, so we will be able to know that one as well. Next is to compact neutron detectors improve feedback accuracy. So the older times didn't have the option to have the neutron energy spectra. So the compact neutron detectors, they can provide with this option that they can give us the energy spectra for the neutron, and they can also improve the accuracy as well. But there are some drawbacks in this as well. So due to not having real-time monitoring, so Friedman and Gemini's in their paper, they said that the crew showed elevated cancer mortality among the crews, and also, the another drawback is neutron dosimetry remains less developed than gamma detection. So neutron dosimetry is complicated because neutrons are uncharged particles. They are indirectly ionizing, and so we can detect gamma very quickly. But to have the dosimetry for the neutrons, it's quite difficult as well. The second is the shielding strategies and material innovations. So as I mentioned before, that lead and concrete are our traditional shielding materials, but they are quite heavy and we cannot incorporate them into submarines due to the weight constraint. So that is why we have polymer and gadolinium based composites. So gadolinium is effective because it has more neutron absorption, and we need to have that in the submarines because since it's in neutron and gamma radiation. So polymer and gadolinium based composites, they are lightweight as well as they are effective as well. Similarly with the boron fill polymers. So boron fill polymers, they also have higher neutron absorption and they can attenuate the gamma radiation as well. Next is the bisphenol A composites. So the bisphenol A composites, they have multifunctional properties. So first is that they can have a good mechanical strength, and the second is they can attenuate the gamma radiation. So recently we having hybrid layers. So the hybrid layers, so they can have higher neutron absorption, and they have higher gamma attenuation as well. So we are currently into this hybrid layers, so they can replace the traditional lead and concrete shielding. Next is the simulation and computational modeling. So the only problem with the submarine data is that it is really classified. So it is really hard to get the data. So that is why we are developing simulation and the computational modeling. So Monte Carlo and hybrid deterministic codes are the important ones. So Monte Carlo have implemented NNCP fits into their modeling. So this codes, they can take into consideration the material interactions when they move. So we will be able to know how gamma and neutrons scatter, absorb into the materials. So we will be able to know. So with these simulations, we will be able to we can virtually see how the compartments are, or how much dose the crews can get within their dose distribution and their dose estimation. But the only challenges and the only limitation is that the classified submarine geometry and the validation data and the model uncertainty as well. So the next is the accidents and the environmental monitoring. Although we have the shielding and everything is according to what we want, since it's an so the accidents are prone to happen. It's uncertain. So we can go back to 2000, where about the Kursk submarine case, where there was a highly radioactive leakage into the seawater, and which was really so to detect the radioactive or radionuclide in the seawater was really difficult as well. Barno, in his literature review, said that environmental monitoring was when this happened, so the monitoring was done by the gamma spectrometry. So when all this happens, IEA emphasizes to be prepared and to handle the marine contamination by modeling. So we can do this by integrating all the AI models as well. And another drawback is that in distinguishing the neutron and the gamma biological effects. So as we know, the neutron has higher RBE. The next is that Russia, which was former the Soviet Union, has had the greatest number of the nuclear submarine accidents because they manufacture or because they have higher number of nuclear submarines as well. So the next is the strategic and policy development. So two protection standards that have been developed are ICRP and IEA. So they set the radiation dose, they set the standards for the protection. As we all know that Australia has undertaken the construction for the nuclear submarine with its partnership with UK and USA as well, which is currently happening in Adelaide, and which is, I think it's going to be get done by 2040, hopefully. So Holbert in his paper said that radiation protection must be integral to submarine design. So so the radiation protection must be taken into consideration beforehand and not after everything is done. So the next is limitation and research gaps. So the major drawback is the classified data. So we are not, so we don't have the access to the dose data on the submarines. So that is a major drawback. Also, it is due to the inadequate neutron dosimetry validation as well. The next is the uncertainties in biological effectiveness of neutron radiation, and marine radionuclide detection still lacks sensitivity. Since neutron doesn't have any charge, and since it has higher biological effectiveness, it's really difficult to detect the neutron as well. So moving on to conclusion, radiation in submarines is complex, but it is improving day by day. So as we saw with the advancements in the materials, in the modeling, and in AI and robotics, we have been trying to develop more materials and to ensure more safety and more protection. Also, the international standards, they come up with the rules and regulations to ensure consistency and safety culture. So for me, for the future work, what I've been focusing on the transparency, how the data and how the doses vary. So data sharing and the multi-technology integration as well. Thank you.
Hey, thank you. Any questions?
Very interesting subject. Thank you. Hybrid layers. Can you explain more?
Hybrid layers?
Yes.
So we are developing the layers of composites. So one that can have neutrons, so one that can absorb more neutron, and one that can attenuate the gamma. So two in one, so they are lightweight as well, and they can be more effective as well. So instead of lead and concrete, we can also have the hybrid layers as well.
Yeah, Martin or Joel. Martin, do you want to jump in?
Sure. Thanks, Clarissa. That was really interesting. It's a really challenging area to be working in. It's not that clear to me exactly what you're going to produce in this project. Is it basically you're doing a review of the area? Is that what you will produce?
Yeah, for now it's the review because I don't have any data regarding the submarines. It's really classified. So for now, I'm focusing on the review, but I have plans to have the 3D printing of the submarines to elaborate more on the radiation protection and where is the more hotspot areas as well.
Do you know at least what type of reactors they are? Whether they're fast or moderated reactors? What do you know what is typically used?
Do you know what type of reactors are typically used? do you at least know that information about the submarine?
Sure. So
I think online we've lost audio. Has someone muted the microphone?
Yeah. My bad. We got kicked out of our own meeting.
Fair enough.
Can you hear us?
Yes, can hear you now.
Okay, yeah. What did you miss? Actually, I'm probably gonna
Oh,
start.
I just got
No,
I
it's
just got
still going.
I just got to the end of the question about what type of reactor, and then was it?
So did you miss everything after that, Martin?
No, we lost it at that point.
Okay, she just said she's gonna investigate it. Yeah.
Sure. Yep.
Good question.
Yeah,
Josh.
yeah, excellent. I was asking, how much do you think like non-submarine studies into shielding and reactor shielding would translate to this?
not a submarine.
Yeah, non-submarine studies, this means that still getting useful information to address the limitations of classified.
Yeah, so basically for the submarine data, I was not able to find the papers as well. So I integrated other ones. So the composites and the polymers were not taken from the submarine. So it's all individual studies. So non-submarine data, if they are relevant to the submarine, we can integrate them as well.
Yeah, so yeah, you can.
Yeah, you can. Yeah. So if they are related to the shielding, so the composites and the polymers, they are not specifically for the submarine as well. They were an individual studies. So I integrated into them and they are quite effective as well as per the literature review that I.
Thanks, Joel. I have a quick question, actually. So I'm a bit confused about your inclusion criteria for your studies, because you said that you were only going to include studies for the last 10 years, but you've cited quite a few studies that are way earlier than that. So I guess my question is, first of all, why are you only including the last 10 years? And if you are, why are you including studies that go back way past 10 years? Because you mentioned an incident from the 2000s, which is obviously greater than 10 years ago.
Yeah. So I looked into 10 years because every day there's a new developments about the polymers and the composites and the new shielding technologies. But I mentioned the 2000 incident just to have so how the seawater radionuclide detection is still a problem. And about the 10 years is to just give how we are developing into more and more technologies. Just to like that.
Okay. I think I'd probably suggest not limiting it to the last 10 years.
Okay.
Because you've presented data in your presentation today that's clearly relevant to your study, that was published earlier than 10 years ago. So I'd probably expect that. But you have a quick question. No, okay, all good. That's it. Thanks very much. I guess we can just cut that out.